Now today's topic is motion on plane curves. In this we will consider the motion of a particle on a smooth plane curve, in which we didn't consider the frictional force, roughness of the surface and so on. Now let us suppose that the position of a particle on a curve at any time t be P. This is P point, and with the arc length S measured from a fixed point P1. Even on the arc, this curve P1, P, this is arc or a curve, this is a curve, and the part of a curve is called arc. So in this curve we have taken P1 as the fixed point. So every distance will be measured from this fixed point P1, and P is any point with arc length S measured from this fixed point P1. Let V be the velocity at P, and X and Y are the components of the forces acting on the particle along the coordinate axis. A normal reaction R acts at P on the particle because the curve is smooth. So here only a normal reaction will act on the curve. Now on resolving these forces along the tangent at P, we have, so in tangential direction acceleration is v dv by ds. So force will be m v dv by ds, and along tangent the components of the forces will be, here we have two forces, x force along the x-axis and y force along the y-axis, and this tangent is making angle psi with the x-axis. So the component of this x along the tangent will be x cos psi. In same way, here the angle between y and tangent will be 90 minus psi. So the component of the y along the tangent will be x sin psi. So we have equation 1 for the motion along the tangent. But as we know that cos psi is dx by ds and sin psi is dy by ds. So putting these values, we get next equation. Now on integrating this with respect to s, as shown here, so we get in left hand side ds will be cancelled out, we get mv dv. So on integration this will give 1 by 2 mv square, and in right hand side we have integral capital X dx plus y dy plus c1. Now let us take x dx plus y dy as phi of xy, where we can write this is d of phi. This is d of phi. D of phi of xy, so we can write d phi equal to del phi by del x dx plus del phi by del y dy. So on equating we get capital X equal to del phi by del x and capital Y equal to del phi by del y. So on putting this we get this one, and simply this is d phi. So on integration we get 1 by 2 mv square equal to phi xy plus c1. Here this phi xy is known as the work function, and 1 by mv square gives the kinetic energy of the particle at the point P. Now let initially the mass of the particle is m, and it starts with the velocity v0. Then using initial condition we have P1 x naught at the point P1 x naught y naught. We have equation 4. Now from equation 3 and 4, on eliminating C1, we get, or subtracting these two equations, we get equation 5. Now the right hand side of the fifth equation shows the work done in moving particle from the point P1 to P, whereas the left hand side shows the change in the kinetic energy of the particle. So the change in kinetic energy is equal to the work done by the total external forces. This is the result. Change in kinetic energy is equal to the work done by the total external forces. And the equation 5 is also called energy equation, and the forces of this type are called conservative forces. Now the potential energy of the particle is given by the formula. Potential energy at point P is integral x y to x dash y dash capital X dx plus y dy, where x dash y dash be the standard position of the particle and x y be the position of the particle from which it moves to the point x dash y dash. Now conservation of energy. Now the potential energy of the particle at P, as we done in previous article related to kinetic energy, we can put capital X equal to del phi by del x, delta y equal to del phi by del y, and so we get this thing on integration. X capital X dx plus y dy is d phi, so on integration we get phi, and limit is from point xy to x dash y dash, so we have phi x dash y dash minus phi of xy. But we know that the kinetic energy is given by 1 by 2 mv square equal to phi xy plus c1. So on adding these two, we have kinetic energy plus potential energy is equal to phi x dash y dash plus c1, and so we can see from here that kinetic energy, the sum of kinetic energy and potential energy is constant. Now next article is motion in a smooth vertical circle. Now particle is attached to one end of a light inextensible string whose other end is fixed. It is projected horizontally with a given velocity u from the vertical position of the equilibrium. Now let O be the fixed point. O is the center of the circle, and one end of the light inextensible string of length L is fixed at O. Here we have OP as string whose one having one at fixed at the point O. A mass M is attached to the other end of the string, and on the other end there is a mass M. Now mass will act along the downward direction. Now initially particle be at P1, now it is projected horizontally with the velocity u. Let the particle be at P and at time t, and the angle P1 OP. Now initial position is P1 and after time t it is at P, and the distance between these two positions is P1 OP is angle between these two positions, that is P1 OP is theta. Now P1 P is the S arc length covered in time t, and V is the velocity of the particle at the point P. Now external forces are the weight mg acting vertically downward and tension T in the string acting along the string along the direction PO. So the equation of motion will be forces along tangential direction, So m d2s by dt square equal to minus mg sin theta. So this angle is theta. So we can see here this angle is theta, then this angle is 90 degree, and this angle will be also theta. This is theta. If we extend this, yes, this if we extend the line of the force mg, and then this will be perpendicular to this OP2, and from this triangle OPP2 we can see that this angle is theta, then this angle will be 90 minus theta, and so this is theta. Yes, this angle will be theta, and from vertically opposite angle this angle will also be theta. So, and its direction is opposite to the direction of tangent. So here I have taken negative sign. So the equation of motion along the tangential direction will be m d2s by dt square equal to minus mg sin theta. In same way, along the normal direction we have, along PO, T is tension, that is also along normal direction. So mv square by rho equal to T minus mg cos theta. Now, as we know that in a circle, arc length equal to angle upon radius. Arc length is equal to angle is equal to arc upon radius. Angle theta equal to arc upon radius. Here arc is S and radius is L, length of the string. So we have S equal to L theta, and this implies V equal to ds by d theta equal theta, and dt equal to L d theta by dt, and this again implies d2s by dt square equal to L d2 theta by dt square. Now from equation 1 and 3 we have L d2 theta by dt square equal to minus g sin theta, and multiplying both sides of this equation by 2L d theta by dt and integrating, we get v square equal to L d theta by dt whole square equal to 2Lg cos theta plus c1. Now initially at point P1 we have theta equal to 0 and initial velocity is equal to u. So this will give the value of the constant of integration, and putting this value we get the velocity of the particle at the point P. Now for the circle, we have radius of curvature equal to radius of the circle. So we have in this case rho equal to L. Now again from equation 4 and 2, using rho equal to L and V square equal to this one, we get T equal to given by this. You have to learn this equation relation for the motion on a particle on a circle. Now equation 4 and 5 gives the motion of the particle. Now at the highest point P1 dash, we have theta equal to pi, in this highest point. Particle started from the point P1 where we have taken theta equal to 0. After covering the semicircle, it becomes at P1 dash. So in for the P1 dash we have theta equal to pi. So at the highest point P1 dash, theta equal to pi, then the equation of the motion becomes this one on putting the value of theta. Cos pi is -1. So we get this thing. Cos pi is -1, so we get velocity from this equation. Now next, at the highest point we have T equal to m by L u square minus 5 Lg. So you have to also learn this. Next, now if u square is greater than 5 Lg, then from the relation of T or v square, from equation 4 and 5, we can see if u square, if greater than, or also from 6 and 7, from equation 6 and 7, if u square is greater than 5 Lg, then T is also not 0 and V is also not 0. Then neither V nor T is 0 and the particle will complete the motion along the circle. Now again, if u square equal to 5 Lg, then from the relation, from the expression of T, we can see that T equal to 0 in this case, but V is not equal to 0. So the string slacks for a moment at P1 dash and the particle also completes the circle. And so for u square greater than equal to 5 Lg, the particle describes the complete circle, and that is the least velocity of the projection to describe a complete circle is under root of 5 Lg. You have to learn this expression. यानी जो लीस्ट वेलोसिटी है जिसके थ्रू पार्टिकल को प्रोजेक्ट किया जाए और वो पूरा सर्कल डिस्क्राइब करे, दैट इज दिस वन. 5 multiplied by radius of the circle into g. You have to learn this value also. Now let v equal to 0 at theta equal to theta 1. Now we have to find when particle stops. So v equal to 0 at theta equal to theta 1, we have from this relation we get the value of theta 1 as cos theta 1 equal to this one. Now again, suppose t equal to 0 at theta equal to theta 2, when tension is 0, then for putting t equal to 0 in the expression for the t, we get cos theta equal to this one. Now let's suppose h1 and h2 are the height of the particle above the point P1 where velocities and tensions vanishes respectively, then h1 will be OP1 minus L cos theta 1, and putting the value of theta 1 we get this thing, h1 will be u square upon 2g. तो ये एक्सप्रेशन भी आपको लर्न करना पड़ेगा. इट इज द हाइट व्हेन द velocity of the particle vanishes. Again same way, when the tension vanishes we have the height h2 is equal to this one. Now we have the following cases for the discussion. Case 1, when the velocity vanishes before the tension. It means h1 is less than h2. The height at which velocity becomes 0 is less than the height at which tension becomes 0. So in that case we have u square upon 2g less than u square plus lg upon 3g. After simplification we get u less than under root of 12g, and then cos theta equal to positive. So theta 1 is acute angle. So for u less than under root of 2lg, the particles comes to rest for a moment below P1 dash and comes back to the original path, that is it oscillates along about the point P1. It means in this case if particle starts from the point P1, and when it attains the height h1, particle is moving this, when it attains the height h1, then it stops and it turns back, and again here it attains height h1, then it stops and again turns back. So it will start oscillating along the point P1. Next case, velocity and tension vanishes simultaneously. दोनों चीज एक साथ ही अगर vanish हो जा रही हैं, then we have h1 equal to h2. On equating these two values, we get u equal to under root of 2lg. In that case, cos theta equal to cos theta 1 equal to cos theta 2 equal to 0, and this implies theta 1 equal to theta 2 equal to pi by 2. So for u equal to under root of lg, the particle rises up to P2 and then come back to original path, and it oscillates about P1 in semicircular path. क्योंकि यहाँ पे theta 1 equal to theta 2 आ रहा है, यानी कि when particle covers 90 degree angle, then here particle starts from this one, and when theta becomes 90 degree, tension and velocity both vanishes, so it comes back. Again here theta becomes 90 degree, so it again come back, so it oscillates about point P1 in semicircle. Now next, third case, when tension vanishes before the velocity. In this case we have h1 greater than h2, that is u greater than under root of 2lg, and in this case cos theta is negative, so theta 2 will be obtuse angle, and when t equal to 0 the string becomes slack. टेंशन 0 होने का मतलब क्या है कि स्ट्रिंग टूट जाएगी, बट वेलोसिटी इज नॉट 0, सो द पार्टिकल डिस्क्राइब्स द पाथ फॉर u lying between these two values. So this is all about the cases for the motion of particle on the plane curve in circular path. So this is the end of this session. Thank you.